I thought I would do a quick video of graphing functions. Chapter 3 test is basically just about graphing. There's some other things that we did at the beginning with polynomials, but really it was in essence of building up to graphing. So here are a couple quick things about graphing functions, polynomials, and rationals. So when we're graphing polynomials, step one, first thing you got to do is you got to find your x-intercepts. And that's what kind of takes a really long time with polynomials, right? If it's in factored form, then it's actually a lot quicker because you're just asking yourself, what do I plug in for x that makes it 0? That's what x-intercepts mean, right? What do I plug in for x that makes the equation 0? Because when the equation equals 0, that means your y value is 0. So you're finding what are the x values that make my equation 0. That's finding the x-intercepts. Once you find those x-intercepts, then two, you just start plotting points. Okay, that's the basic easy way to do it. Okay, there's some things that you can look at. You can look at the degree of the polynomial, and that will tell you kind of what the shape generally looks like. You could look at the leading coefficient, and that will help determine kind of the shape. You could look at the x-intercepts and what their multiplicity is, how many factors of each type you have, and that will kind of help you graph. But really, if you find the x-intercepts, so here's a quick example. I'll give a detailed more example in a little bit, but I thought I'd go through both of these really quick, and then I could do an actual example if you need more help. So if I have my x-intercept, say right here, okay, then I just plot points. I pick an x, I plug it into my equation, I see is the y value up here or is it down here? Okay, then I pick a number in here. Is my point up here or is it in here? If you want to, you can actually graph the points. But even in this, with these rough sketches, we really don't have to. I pick an x over here, I plot it. Is it up above or is it below? I pick a point after. Is it above or it's below? Then if it is above to the farthest to the left here, then we would graph up here. Okay? If it's not, if that point is not up there and it's down below, then we would graph right down here. If it was above, say up here, then we would just graph above. If our point was down below on this one, then we would graph below. Okay? If it wasn't, if it was also above, then we would graph above. And I don't care how far up and down you go. This is just basic. In calculus, we'll get into more detailed those local mins and maxes. Okay, and then say if it was the last part was down below, then you go below and you draw your arrow. And so that's basically how you can graph your x-intercepts and plot your points. I'll go into more detail in a little bit of how you find your x-intercepts with polynomials. Okay, rationals, first thing you want to do is you want to find your vertical asymptotes. Right? And there we set the denominator equal to 0. Right? So we set it equal to 2. No, equal to 0. That's a 0 there. So we set it equal to 0, right? And now we'll find us our vertical asymptotes. Sometimes we don't have vertical asymptotes, we might have holes. That's the case of if I factor and I have x plus 1, say x minus 1, and then on bottom I have x plus 2 and an x plus 1 when I factor it. So my vertical asymptotes, I set the denominators equal to 0, so x equals negative 2 and x equals negative 1. But because on this one, x equals negative 1, but because these two are the same, that means this 0 is not a 0. It's not a vertical asymptote. It's actually a hole. Okay? But that's how we find vertical asymptotes. Okay? And never can our graph cross a vertical asymptote. Okay? Once we find the vertical asymptote, we can graph it, and then step 2 is find horizontal asymptote. And this is where we look at the degree of the numerator and the degree of the denominator. Okay, and if the degree of the denominator is bigger than that of the numerator, then it is always y equals 0. If it is the same, that means then we have y equals the lead coefficient of the numerator over the lead coefficient of the denominator. Okay, if the numerator is bigger, has a bigger degree than that of the denominator, Then we have an oblique or a slant asymptote, and I kind of showed you in class or on a video how to do that. But here we have an oblique. There might be an I before that. Oblique asymptote, right? And we don't really have to worry about those too much right now. Calculus will get into it, but you find those usually you don't have a horizontal asymptote here, or it's called a slant asymptote. That's when you might have an x squared on top and only an x on bottom, so you can do synthetic division or long division to find it. If it's more than 1 degree, then they say that you have no horizontal asymptote. But we're not really dealing with those. Anytime your numerator is greater than your denominator, you're going to have an oblique asymptote or a slant asymptote. Okay, so that, and then once you have those, you're pretty much done. Now step 3 is to plot points. Okay, so once you have your vertical asymptote, say here and here, right? Then I just plot points. I pick an x over here, plug it in, see what I get. Put an x here, plug it in, see what I get. Put an x here, plug it in, see what I get. And then you have your horizontal asymptote, usually y equals 0 most times, right? When the degree of the denominator is bigger than that of the numerator. Okay, so then I just plot points. And if I don't know what I'm doing, then plot more and more points to see kind of what the graph looks like. When I say plot points, that means I'm picking an x. Okay, so if this is x equals, say 2, and this is x equals 5. So I might pick 0 and plug it into my original equation. So I'd plug in f of 0. That means I'm plugging in 0 for x into my function and seeing what's the y value. Go ahead and plot that point. Now pick, say, 3, plug that in. Pick 6, plug that in, see what you get. Now remember, we just have to find out where it's kind of located, because we know once we have it, say it's up here, it's going to always approach the vertical asymptotes, right? If it's down here, then I know it's going to approach this one. Okay? It's always going to approach those vertical asymptotes. The only thing we have to worry about, right, would be step 4, and it's okay, not all the time that it's okay that you can skip step 4, but step 4 is taking your horizontal asymptote and setting it equal to your function. Okay, and I'll explain that a little bit. And that lets you know, does it cross your horizontal asymptote or not, right? But it's always going to approach these asymptotes. So maybe you do cross it, but eventually it's going to come back down, and it's going to approach that horizontal asymptote. So if my point's up here, then I know it's going to approach this one and approach the vertical. If it's down here, then it's going to approach this one and approach this one. And another thing I can look at more detail is if this vertical asymptote has a multiplicity of 1, that means if this side came up, the opposite side of this vertical asymptote must go down. If it's an even one, or multiplicity of an even number, so multiplicity of 2, multiplicity of 3, if this side goes up, then on the other side must go up. Okay, so that's how you can use multiplicity. But basically, the basic thing, you find your vertical asymptotes, you find your horizontal, and then you start plotting in points. And then when you graph, you can graph more than 1 point. I don't care how many points you graph in between. It doesn't matter. But all you really need is 1, and you can use some other things to help you graph, right? But if you don't know, just plot more points, because we always approach the horizontal asymptote, and we always approach the vertical, right? So I can't approach it both ways, all right? I can't approach the vertical this way and the vertical this way. All right, so that's a quick 10-minute video of kind of how to graph. Okay, now I'm going to go ahead and actually put up some problems. So those that want to stick around or watch it, you can. I'll do a couple examples, or at least one example for both of these. Okay, so here's a polynomial that asks to graph. Okay, and so I have to find the x-intercepts, right? That's the first step, is find x-intercepts. So how you do that is you take the factors of your constant. Okay, that's the number without the variable. Okay, and I got to list those. Okay, so that's 1, 2, 4, and 8, right? And then I got to divide each of those by the factors of your lead coefficient. That's the coefficient in front of the largest exponent. Okay, so that'd be 1 and 3. Okay. So we have 1, 2, 4, and 8, and 1 and 3 are the factors of the lead coefficient. Now, that's not my answers, and that's all. Remember, these are the possible rational solutions, and that's all you need to find. So this is kind of like the second or third problem from your quiz part 1. You were asked to find just list the possible rational functions and then find what are the actual rational solutions, okay? Because when we're graphing here, it's really hard to graph the irrational ones, right? And we can't graph the imaginary ones, so we just want to find what are the rational ones. Okay, so to find the possibilities, we take these 4, and we're going to divide them by 1. So that's 1, 2, 4, and 8. Then I want to take these 4 again and divide them by 3. So that is 1/3, 2/3, 4/3, and 8/3. Okay, and then they are all plus and minus. So how you can tell how many you're supposed to have is take how many factors are in the constant, which here was 4. How many factors were in the lead coefficient? That's 2. So 4 times 2 is 8. So there should be 8 of them, and then times it by 2 because plus and minus. So 1, 2, 3, 4, 5, 6, 7, 8. So there's 8, and then it's all plus and minus. So that is a total of 16, right? Okay, so there's all of them. Then you can check to see, is there any that are the same, right? 1/3, 2/3, 4/3, 8/3. None of them are the same. So those are our possible rational solutions, okay? Possible rationals. Now to actually find which ones are rational, we have to take our coefficients, and we're going to run through synthetic division until we find all. So now we want to find all rational solutions. Okay, that's what I want to do now, is find all rational solutions. So I take my coefficients, I'll write them again, and start running through these possibilities into this box, right? So I always want to start with 1, because if I start with 1, that's it. Sometimes it's always 1, right? So 3, so -4, -4, that's -10, and -10, it is +2. So that doesn't work. So we're going to have to try another one. Well, we can try -1. So how about -1? So we can erase these. So this is what sucks, right? Because you have to keep on going, erase, erase, do more and more problems, more problems. Then if you mess up in your multiplication, you have to restart the whole thing. I understand these are a pain. So -10, it's +1. Oh, +1. See, if I mess up, then I would forget about 1 and it didn't work. Then I have to come back later. That's a +10, right? 4, that's not going to work because that's -4, that's 8. So that's not going to work. Okay. So you just got to keep going until you find them. So I'm going to pause and I'm going to do it myself until I find one. Okay, so I haven't found one yet, but when I plugged in -2, my new coefficients down here goes positive, negative, positive, negative. And because this is a negative, and because these alternate between positive and negative or negative, positive, negative, positive, that means there's nothing smaller than -2 that's going to work. So I can eliminate anything smaller than -2. So if I come up here, that means I can eliminate. That means I can eliminate this -4 and this -8. I can also eliminate 8. 8 divided by 3 is 2 point something, right? So I can eliminate that negative as well. So there, it just eliminated some for us. So that's good. Okay, still haven't found one, but here's another thing. So I plugged in a +4 and I got all positives down here. Because this is positive and we got all positive, what that means is there's nothing greater than 4 that will be a 0. So that means I can eliminate 4 now. I can eliminate 8. I can eliminate, can't eliminate 8/3 yet because 8/3 is not greater than 4. So I can't eliminate that. We already tried, I already tried. So we're probably going to have fractions next. So I'm going to have to enter in some fractions. So I'll try those out. But at least I eliminated those, right? Without even trying them. So I eliminated 1, 2, 3, 4, 4 without even having to try them. Oh, and it probably would also help if you actually listed all the coefficients before you run through every one of these, which I didn't run through all of them, but I forgot the 8 here. So I forgot the 8 here, so let's go ahead and try 2. So that's -1, that's -2, that's -8, that's -16, that's a -4, that's a -8, and 0. So hey, look, 2 worked when I didn't think 2 worked. So make sure you have all the coefficients, right? So I understand your frustration when stuff doesn't work and all you did was a simple mistake, right? So 3, so now we could try 2 again, because maybe there's a multiplicity, right? So maybe there's a multiplicity going on. So we'll try 6 is 5 is 10 is 2 is +4 is 0. So we do have a multiplicity of 2. So now we have 3 terms. Since we have 3 coefficients here, we could do not synthetic division, sorry. We can keep going, yes, we can keep going with synthetic division if you want. You could try 2 again, see if that works. Remember, these are all positives, right? So positive's probably not going to work here because these are all positive, right? And because we have a positive here, 2, and those are all positive, so probably nothing greater than 2 is going to work. So what we might want to do is quadratic formula or factoring. We kind of don't really want to do quadratic formula because we want rational solutions. I mean, you still can, but we don't care about all the solutions. We just care about the rational ones. So you could probably CAB it, right? CA and your B, 3 times 2 is 6, 5. What are the factors of 6 that add up to 5? That would be 2 and 3. So 2 and 3. Divide those by your A, which is 3. So we get 1 and 2/3 is our factors. Now these are our factors, right? And so then our actual zeros would be -2/3, x equals -2/3, and x equals -1. And then we had x equals 2 with a multiplicity of 2, right? Or you can just write it twice. So I could list them as factors. So they're the factors, and I can x minus 2 quantity squared, right? So I could write this as in factored form. So this is factored form. That's kind of the easy way to find your x-intercepts, because all we have to ask ourselves is what minus 2 is 0? That's +2, right? What plus 2/3 is 0? That's -2/3. What plus 1 is 0? That's -1. So then you automatically found your x-intercepts, right? And you could graph those. That's why factored form is really kind of the easiest way to graph, because they almost hand you the x-intercepts. So here's our x-intercepts, -1, +2. So let's put some points down. X-intercepts, and then -2/3, so that's -0.67. So maybe somewhere about right here. Okay. All right, so that was step 1. That's the longest process, right? Now we just have to plot points. So I pick some x's, I pick one over here, and see what I get. Sometimes you could plug these back into synthetic division, your original synthetic division, your original coefficients. You could put them back into your factored form here. Right? You could plug these x's that you pick into factored form and see if you get a positive or a negative. Right? I like to do that. You could plug them back into the original, just plugging them way back here. Plug in your x here, your x here, your x here, and your x here. That's a cube. Plug in your x's all there, right, and find it out. You could do synthetic division. There's an 8 there, right? And you could start plugging those in. So I could pick a point, run through whatever you get at the end, your remainder. That's your y value, and you could plot that point, right? But I like to do factored form because I'm just looking for positive and negatives. I don't really care what the actual y value is. I just care, is it positive or it's negative. So I want to plug in a negative, say 2. Okay, I want to see what I get. So let's plug in a -2. And let's see what I get. Actually, I might have already done that, right? So here's where you can really use what you missed on synthetic division, right? What you didn't get 0 out. Those are actually points, right? So when I actually plugged in -2 to begin with, I got a -6, I got -13, right? I got a +26, so I got a +20. And -2 times is -40, right? And so that's a negative 28. Multiply that by negative 2, that's like 56. And plus 8 is 64. So notice I got a positive out, right? So I could plot that point negative 2, 64, but that 64 is a really big number, right? So at negative 2, I know it's positive, right? So I know this graph is going to go up, and I can tell that actually from right here, it's to the fourth, and it's a positive lead coefficient. So I know it's going to go up to the left. So from this last endpoint, I know it's going to go up. So you could graph that point negative 2, 64, but just draw your graph up. And that's all I care about, kind of just the rough sketch. All right. And then I can plug in a number in between. That's kind of going to be hard, right? So that's like 0.7. Ugh, 0.7. But we could do that. This is factored form is probably the best for this. All right, because negative 0.7. Let's get that correct. Negative 0.7. So negative 0.7. It's quantity squared. So this is great because it's squared. Anything, a negative or a positive in here, it's always going to be positive, right? And then a negative 0.7 plus 2/3. Well, 2/3 is 0.67. This is 0.7, so negative 0.7 is bigger. So this is going to be negative. And then negative 0.7 plus 1. 1's bigger, so it's going to be positive, right? And I have a positive times a negative times a positive is a negative. So I know in between here, it's going to go below. So it's going to go below. It's going to be below the x-axis there. All right, now I can go ahead and plug, say, a 0 in or 1. 0 is really easy to plug into the very beginning, right? So if you plug in 0 to the very beginning, these are all going to be 0, right? And I get plus 8. So I know I'm above. If you want to, you could really graph that point plus 8. But I'm okay with you not necessarily graphing that. If you want to, it's going to go something like this, right? And come back to this point. Okay, now what happens after that x-intercept? So let's plug in, 3. So 3, you can plug it into synthetic division, you can plug it into the original, you can plug it into factored form. I'm going to do factored form on this one. Usually when I have things other than 0, I usually do factored form just because it seems easier to me. Because all I look at is the positives or negatives and then multiply them. This is squared. So it doesn't matter. I know every time this is always going to be positive, right? Because I'm squaring it. So I don't even really have to worry about that one. 3 plus 1. These are all positives, right? So it's positive, positive, positive. This is going to be positive, so it's coming up. And I could tell that again because it's the degree 4. So it's going to either go up and up at the ends. Out here and out here, it's going to go up and up. Or it's going to go down and down. And since it's a positive lead coefficient, it's going to go up and up. Okay? So there's the rough sketch. It's done. Another quick thing, just quick note on this. Because this had a multiplicity of 1 and this had a multiplicity of 1, that means it's going to go through that x-intercept. But because this one had a multiplicity of 2, it bounced off. Okay? So you could use that fact as well. And then I wouldn't really have to, I would just have to find out kind of what's happening in between one of those. But again, you can just plot points. You can plot points every time you can plot points. So anytime it has an even multiplicity, it's going to bounce off. Anytime it has an odd multiplicity, it's going to go through the x-intercept. All right, so here's a rational function. Just going to do one of these. Because I'm supposed to be leaving now, but I'll finish this problem. Okay, so first thing, vertical asymptotes, right? So when we find vertical asymptotes, we set the denominator equal to 0. There's an x here. And then we find what makes the denominator 0, right? That's vertical asymptotes. Okay, if you set the numerator equal to 0, you're only finding x-intercepts, which can be handy because you can plot those points. Okay, since these are squared, we do want to factor, right? So I do want to factor and find any common factors, right? Because if I have a common factor on top as on bottom, then that is not a vertical asymptote on the bottom one. It would be a hole. So if we can factor these, that'd be great. Okay, so there are the factors 3x plus 6 and x minus 4, and the bottom one here is x minus 5 and x plus 1/2. I could move this and do 5x plus 1, but I'm just going to leave it as that because it's just easier. because when I set the denominator equal to 0, I get x equals 5 and x equals negative 1/5. Now both of these are vertical asymptotes because the top is x plus 6 over 3 is x plus 1/2, and x minus 4. Those are my factors, right? And they're not the same. None of these factors are the same, right? So, but if you set these equal to 0, then I get x equals negative 1/2 and x equals 4. Those are x-intercepts. So those are my x-intercepts. So I could plot those points. That could help, right? But that doesn't find my vertical asymptotes. Vertical asymptotes is setting the denominator equal to 0. Okay? So we get 5 and we get negative 5. Now we have to find the horizontal asymptotes. Okay? And that is not setting the numerator equal to 0. That is looking at the degree of the numerator and the degree of the denominator. And because they're the same, we take the lead coefficient, y equals the lead coefficient of the numerator, and divide that by the lead coefficient of the denominator. So y equals 3/5. So that is a horizontal line going through the y value of 3/5. Okay, if the denominator was bigger, degree was bigger, then it would be y equals 0. If the numerator is bigger, then we actually have to synthetically divide to find the oblique asymptote. Okay, so really this is enough information. Okay, we only have to do one check, and we can do that in a little bit. That is taking the horizontal asymptote 3/5 and setting it equal to our function, which we can use the reduced form. Okay, which is 3x plus 6 and x minus 4 over x plus 5. Oh, x minus 5. Must be x minus 5. And 5x plus 1. Right? So maybe I'll just do this now since I'm setting it up. Okay, so then we have to multiply, right? This is a proportion, so I need to get rid of this denominator, so I need to multiply by the denominator. So I multiply by x minus 5, x plus 5, or 5x. Right, so those are going to cancel, but I need to do it to the other side. So x minus 5 and 5x plus 1. And then I need to get rid of this denominator over here, so I multiply both sides by 5, and that cancels that, and that cancels that. So then we have this, so it might have been actually easier to just leave it in standard form rather than factors, because I have x minus 5 and 5x plus 1, and then 5 times, this would be 3 times that, right? 3 times that, and this would be 5 times 3x plus 6 and x minus 4. But so you could leave it in those terms, right? Into the FOILed one, right? Which was so this would be 5 times, because I do have to FOIL this out now, so might as well just left it, right? Because that's 3x squared minus 6x minus 24, and this is 5x squared minus 26x minus 5, and then times that by 3. But you'll notice that if I distribute this 3 to all 3 of them, and I distribute this 5 to all 3 of them, you notice that I get 15x squared and a 15x squared over here, so those are actually going to cancel out. Those will actually cancel out and go away. And then so I just have left negative 78x minus 15 equals negative 30x, and then 5 times negative 120. Okay, so then if we add our add 78x, add 120, so add 78x, add 78x, so that's 48x plus 120 plus 120, 105, divide by 48, divide by 48. So what this tells me is at x equals 105 over 48, so at about 2.2, about approximately 2.2, my graph, my y value will be 3/5. Okay, and I could plot that point. So it is going to cross the horizontal asymptote at 2.2-ish. Okay, so I kind of need that information, right? But now we can start to graph. Okay, so we have a few things. We have our vertical asymptotes, which is at 5 and at 1/5 or -1/5. -1/5. So at 5 and -1/5. Okay. So at 5, let's do 1, 2, 3, 4, 5. And -1/5. So -1/5 is probably somewhere in here, right? So let's go ahead and draw these vertical asymptotes here. So -1/5 is maybe right there, and 5 is right there. Okay, now our horizontal asymptote is 3/5, right? So 3/5 is less than 1, about 0.6, right? So if we do, here's 1, we do 0.6, so a little bit past half, so about right there. And then go ahead and just write down what are they. This is y equals 3/5, this is x equals 5, and this is x equals -1/5. Okay? All right, now we can start plotting points. We plot points in between here, we plot points after, and see where our graph is. We know it's going to cross at 2.2, so at 2.2, we know it's going to hit right here, and that's okay. Okay, so we know it's going to cross there. Now, is it going to cross like this? Or is it going to cross maybe like this? Right? That's the question. Or, I mean, it could cross like this. It could come down here and hit it and then come back up. Maybe that's how it's going to cross. So let's figure it out. The only way we can figure it out is plotting points, right? So if we plug in a, oh, that's not 2. This one, 2.2, somewhere right there. Okay, so somewhere right here it's going to cross. Okay, so we can just start plotting points, right? We do have this point right here. We have some points, right? We have some x-intercepts. We found those. That was at -1/2 and 4. So at -1/2 and 4, can we plot those points? So at 4, we're right here. And at -1/2, at -1/2, correct? Yeah, -1/2. So 4 and -1/2. Right here, right? Oops. Sorry. Okay. So look, we do have some points. So we know the graph, since we have this point right here, we know the graph doesn't cross this line again, right? We know it crosses once right there. So that means it's going to approach the horizontal. It can't cross it because we already have our point that crosses it. And then it's going to approach the vertical. Again, I can't go this way because I'd be crossing it. So that means, oops, sorry. That means that I can't go that way, right? That means I have to go down. Oh, jeez. That means I have to go down. So that means I have to go down. There we go. See, I have one branch already done. Okay. Now the question is, on this one, am I going to come like this, right? Or am I going to maybe hit and then come back down like that, right? So what I can look at is look at the multiplicity of this one, right? This x equals -1/5, right? Was there another x equals -1/5? There wasn't. So that means since this one went down on the left of this vertical asymptote, that means on the right we have to go up. Okay, but if I don't know that, that's okay, right? Because I could plug in 1 into my equation, probably the factored form, definitely the factored form this time, in order to find out what the y value is. Okay, so here's my function. I want to plug in 1, right here, 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 and here. And basically, if it's positive, right? If it would be positive, then I know I'm going up this way, right? If it's negative, then I know I'm coming back down this way. Okay, so you could plot the point. You could figure out what this is, right? So this would be 9. This would be -3. If I multiply those, I get a negative, right? Then I could -27. That's fine. You can put 27 in there. But really, all I care about is positive or negative. Okay, then down here, that's a -4. This is a +6, right? That's multiply, I get a negative, so I'd have a negative over negative, so I should have a positive, right? So that means I should be going this way, just like that. But if you actually want to find out what the value is, right? -4 times a -6 is a -24, and then I could divide this, and it's 1 point something, right? And 1 point something would be above the graph, something around here, right? So I know it's going to come up and approach that vertical asymptote. That means it's going to cross, and this won't have to go down, right? I'm not going to come and swerve down this way. That's not going to happen, right? Because I already plugged in 1 and I got this answer right here, right? So I know I'm not going to come that way. So that means that I'm going to have to come down here. And again, if you could look at this and you could say, okay, well, I approached the vertical asymptote on the left going down, so that means because this only has a multiplicity, right, x equals 5 is only occurs once, that means that this side would have to come up, right? Then I could only approach this one because I can't cross that horizontal because I already know where it crosses right here. So my graph could be done. But again, if we don't know that, that's okay. We're okay with that. Now we can start plugging in x's to the right. You can continue to plug in x's as many times as you want until you know what the shape looks like. Okay, so let's plug in, what's 5, 6? Let's plug in a 6. And again, this is going to be bigger numbers, right? So really you might just think about, hey, what if I just look at positives, right? So when I multiply this is going to be positive, right? When 6 minus 4, that's a positive. And a positive times positive is a positive. What about bottom? That's positive. This is going to be positive, so I have a positive over positive. So that means I should be going up, right? But again, if you want to find out, so over here at 6, I should be going up and should be going down. But again, you could find out what your number is, right? If I was down here, say I got a negative number, that means I would be approaching here and going to the horizontal asymptote there. Okay, but we can go ahead and figure out actually what this number is, right? And that's fine. I'm okay with that. This was y equals 3/5, right? Our horizontal asymptote. Okay, so that's 18. 18 plus 6 is 24, right? 6 minus 4 is 2. So that's a 2. 2 times 24 is 48. That's 6 minus 1 is 1. 6 times 5 is 30. 30 plus 1 is 31. 1 times 31 is 31. So 48 over 31. So 48 divided by 31 is 1.5. So at 6, somewhere right here, at 6 is 1.5. So we're up here. Okay, there you go. Boom. Now you have your graph. All done. Okay, so again, if you needed to go through more, all right, stop by before the test. Don't try to stop by, you know, right before class. So make sure you come in early or when you can.